Okay, so today we're going to talk about Euler's method for approximating the value of a function. Now, this is Euler spelled E-U-L-E-R. Euler spelled O-I-L-E-R is a football team from Texas. All right, used to be anyways, with one of the all-time great running backs, Earl Campbell. But look it up. Euler's method. So here's what we have. We've got a differential equation, and we've got to find the values of a function. And so what Euler's method does is it says, okay, let's say you know 1 point on the curve. Let's say you know 1 point, and you know a derivative. Well, with a derivative and a point, you can get a slope, right? And with a slope and a point, you can get the equation of a line. So theoretically, let's just say this were a positive slope. That could be a tangent line. Now, here's what you learned back in the fall. This tangent line is a really good approximation for the function right around that point, isn't it? Right? So we're going to go a little bit away from that, and let's do the y value on the tangent line. Now, once I get that point, I'm going to calculate another derivative. It's not the same derivative because remember, I know dy dx. So let's say, because remember now, for Euler's method, dy dx is given. And an initial condition is given. An initial point. These are the two things that are given. So basically, what I'm doing is I'm starting with a point that's on the curve. And then I'm going to go a little bit away from that point, recalculate a y value, and then maybe calculate another tangent line. I'm going to go a little bit further, calculate another tangent line, and another tangent line. Then basically what I'm going to end up with is an approximation for the curve. I'll never know the equation of the function, but I'll be able to get the y values so that at some future point, I can say, okay, this is my approximation for that point using Euler's method. Okay, so can you see that? This is the approximation up here. This is the actual value here. And this is what Euler's method does. These little distances here, these increments, are called the delta x's. And you'll usually be told, or you can easily figure out how big they are. Sometimes we call those the steps. Those are called the steps. All right? So this is Euler's method. The key thing you need to remember here, Euler's method, tangent line. When I say Euler's method, you say
tangent line.
That's right, tangent line. You say tangent line. Okay? Why don't we see how this works in action? Now, what I'm going to do is I'm going to show you a problem. The way I'm going to do it is a little bit differently than most textbooks approach this. And that's okay. You feel free to read those textbook authors. They're very nice people, too. I just happen to believe my way's better. Now, why is my way better? My way is better because we're only focusing on tangent line. You don't have to learn anything new. No separate formulas, no separate differentials, just the tangent line. Let's see how it works. 3 columns every time. I want a column for my xy, I want a column for my dy dx, and I want a column for the equation of the tangent line. Now, before we get going with this, let's see what we were given here. We were given dy dx is x plus y. We're given our initial condition, f of 0 is 1. That's an actual point on the actual curve. That's the only one we know. That's it. That's all we know. And I'm asked to find f of 1. I'm also told to take 2 steps. Now let's face it, the AP exam is not going to get overly complicated with this. They just want you to show that you know how to do this. So really, 2 steps, maybe 3 if they're feeling frisky. But it's really just 2 steps. Okay, so therefore that means my delta x is going to be 0.5. I actually figured that out myself. If I go from 0 to 1 in 2 steps, 0.5. All right, here we go. My first point is 0, 1. dy dx, x plus y is 1. All the knuckle draggers upstairs in Algebra 2 will tell you that the equation now is y minus 1 equals 1 times x minus 0. Okay, equation of the tangent line. Now, to go from 0 to 1 in 2 steps, I first land at 0.5. Now, if only I knew what f of x was, I could get a y value for 0.5. But I don't know f of x. But what do I know? The next best thing. Right? Right? There you go. The equation of the tangent line. Here we go. Put in 0.5 to that equation of the tangent line. 0.5 minus 0 is 0.5. Times 1 is 0.5. Plus 1, 1.5. There's your new y value. Now, this is an approximation for the y value, but it's pretty good. Okay, let's get a new dy dx. There's my dy dx equation, x plus y. X plus y gives me a dy dx of 2. Right? Ask the knuckle draggers in Algebra 2. Give me the equation of that line. 2 times x minus 0.5. There's my equation of the tangent line. Next step gets me to 1. Oh my gosh, this is what I want. Here it is. It's coming right now. 1 minus 0.5 is 0.5. Times 2 is 1. Plus 1.5. 2.5, I hope. And that is it, guys. That is Euler's method. That is Euler's method. Now, I've given you a program for your calculator that will allow you to do this in like 10 steps. And as you can probably guess, just like finding the rectangles for area, 10 steps will give you a little bit better approximation than 2 steps will. Okay, but that's what you can use your calculator program for. But just think, and if you run that program on your calculator, what does it ask you for? It asks you for a derivative, it asks you for an initial condition, and it asks you for a delta x, and it asks you where you want to go. And then it will present you a matrix with all of the x and y values. So here we go. The key thing, let's review for just a moment. Euler's method, tangent line. Start with your initial point, your slope, equation of the tangent line. Take your step, plug it into the previous equation. So we take the step, we go up to the equation, then we come back for the y value. Then we take our step, we go to that next equation, and come back for the y value. And that is Euler's method. Feel free to watch this video over and over again. And then do about 100 of these, and you'll be just fine. Have a great day. Euler's method.